All right, one of the things we said last time is that if you have more than one substituent on a six-membered ring, then sometimes you need to draw both chairs in order to assess which one is the most stable chair. And you'll notice that in these two molecules that we've drawn, they have the same basic structure, a six-membered ring, a methyl group on carbon 1, another one on what we've called blue carbon 5. But you'll notice that they're different. They have different shapes. On carbon 1, the methyl group's in the same spot in the molecule above and below, but on carbon 5, one methyl group is up axial and the other is down equatorial. We're actually going to talk about the relationship between these two compounds. They are called stereoisomers because they have the same connectivity but have different 3D shape. And they're a specific kind of stereoisomer, which we'll talk about in a little bit. For right now, it's enough to realize that if you that you've got a down substituent here and an up substituent here versus two down substituents, that's a cis-trans issue with respect to the ring. The substituents are pointing opposite sides of the ring up here, same side of the ring down here. And so you could name these as cis and trans isomers respectively. But let's talk about, but it might be a kind of question that you might encounter would be, which of the following is the most stable chair conformation of this molecule? And when in that situation, all you do is you draw the other chair, and then you compare which groups are axial versus equatorial in whichever chair. Now remember, the way that I'm showing you to flip one chair into the other chair is not the only way, but I find it to be the one that is least distracting. Keep drawing the chair in the exact same way, but remember that on chair flipping, up carbons become down carbons. So we're going to move carbon 1 down to this lower corner. 1, 3, and 5 used to be up carbons, now 1, 3, and 5 are down carbons. If you do that, and then if you know how to draw axial and equatorial substituents on a chair, the chair flipping is going to take care of itself. So on carbon 1, the methyl group was down over here. It's got to still be down on the right, only now it's got the down position on carbon 1 on the right is down axial. Okay, so do you see how that the axial versus equatorial thing just sort of took care of itself by deciding where the carbon 1 was going to be? Okay, and then on carbon 5, we had an up axial substituent. On the right, carbon 5 is a down carbon. The up position is an equatorial position. Okay, so we used to have carbon 1, methyl group was equatorial, now it's down axial. Carbon 5 had an up axial methyl group, now it's up equatorial. So if I were to ask you which of these chairs is most stable, what's the equilibrium constant? Is it favorable or unfavorable? What would you say here? Same. How do you know that? Go ahead. Right, for both of them you've got the same kind of group axial and the same kind of group equatorial. So yeah, you would say equilibrium constant here is close to 1 or exactly 1. Both of those are the most stable chair, right? And you can do this simply by comparing A values, right? The A value tells you how much less favorable it is to have a group that's axial versus equatorial. Methyl group axial here, methyl group axial there, no problem. All right, let's now do the chair below. Again, I won't walk you through this as slowly as we did the one above, but we'll renumber the ring. I will mention that when you renumber the ring, switching where the carbons are up and down positions, it's important that you number the ring in the same sense. So I just screwed up, didn't I? Yeah. If it's clockwise, if you number the ring clockwise on one side, you should continue to number it clockwise on the other side. The why behind that is not immediately apparent, but if you mess that up, you're going to make some stereochemistry mistakes that will become clear later. So As before, methyl group on carbon 1 on the left should now be axial down. Carbon 5 on the left had a down equatorial methyl group. Now that methyl group should also be down axial. All right, so this one should be pretty straightforward. Which one is the most stable chair? Left, right? Because both things were equatorial versus the one on the right. Both things are axial. And if you had to estimate what the delta G would be for having two methyl groups axial versus equatorial, you can estimate that by using A values. You have to pay attention, right? You've got two methyl groups that used to be equatorial, now they're axial. You'd expect this delta G to be at least twice this A value and maybe higher, all right? So 1.7 plus 1.7 equals whatever kilocalories per mole. I can't do math. Why are you asking me to do math? Probably it's worse than that, because remember, these A values come from a single methyl group or a single substituent clashing with two other protons. You got something worse going on here because the two methyl groups are now clashing not with two protons, but with a proton and another methyl group. So I'm not asking you to do the math and predict exactly what it would be, but just have a sense this is probably worse than additive than adding the individual effects of having one methyl group axial. Yeah?
We use the A values, is that because the methyl groups are eclipsed?
Is that because the methyl groups are eclipsed? No, we use the A values come from measuring the equilibrium constant for having the methyl group axial versus equatorial. So we're just using that number directly because we're in that situation. What I was pointing out, though, was that these A values come from monosubstituted cyclohexanes, where the thing that it's clashing with are these other axial protons, whereas in the disubstituted case down here, the methyl group is clashing not just with two other protons, but with another methyl group. So probably it's even worse than we're predicting. Yeah? Do you need to memorize the A values? No, you should be aware of the trends. If you need them, I'll give you the A values. Okay? It would be useful to go through, I'm not going to do this example in class. This may be a repeat of a problem from a study guide or a practice exam. But it would be useful to go through and try to predict what the most stable chair would be for that molecule. So draw the other chair and see if you can figure out which would be the most stable chair. And then the other way you can experience questions in this area is, you look at a question and ask which is the most stable chair for this molecule, and you think it's about just choosing the chair where everything is axial or where everything is equatorial. But the problem is more complicated than that. Let me give you an example of that. Why not? I'm going to draw a carbohydrate here. A carbohydrate is a six-membered ring, kind of like a cyclohexane, only one of the atoms of the ring is an oxygen. But in general, that oxygen doesn't really change the conformations available to this molecule. So, sure, why not? And then I might have options. I'd ask you which is the most stable chair of that molecule. And then I might have options A through J or something like that, examples of possible things to choose. When you're in that situation, you're being taken for a ride because how many chairs are there possible for this molecule? 2. So if there are 10 options, only 2 of them could possibly be the right molecule, right? So what are the other bogus options going to be? They're going to be things that look like this molecule but are different in ways that I will now show you. Don't you love that I'm evil, but I disclose my evil tricks? It's kind of like Dr. Doofenshmirtz monologuing to Perry the Platypus. I can do the voice, but maybe if you're lucky, we'll get to that later. Not if Perry the, well, that one's easy, yeah. All right, so let me show you how to take a drawing of a cyclohexane molecule from above and then make sure you get it right in the molecule below, okay? So first of all, dispense with your anxiety about whether you're drawing the right chair to begin with. It doesn't matter. You're going to draw the one chair and the other chair. So what you need to do is draw a chair and then pick which atom you're going to number, or pick where to start. And let's number the atoms of the ring. We'll start with the oxygen. 1, 2, 3, 4, 5, 6. I'm going clockwise. I simply have to decide where to put the oxygen. So just for fun, I'm going to choose to put the oxygen at this down position. It may or may not be that I've drawn that the chair that I'm going to draw now will be the most stable of the two chairs. Again, doesn't matter, because I'm going to draw both of them and we're going to see. So this is critically important. If you don't do this right, you're going to get it wrong. You've got to number your chair in the same sense that you've numbered the ring above. Then we're simply going to go and follow around the ring and put the groups in the right place, realizing that dashes like this mean that a group is down relative to the ring, whereas wedges like this mean a group is up relative to the ring. So on carbon 2, in our drawing below, carbon 2 is at an up carbon. Which position is down on that up carbon? Is it the axial position or the equatorial position? Equatorial, good. So the OH goes there. Carbon 3, which is a down carbon, has a down OH group. Which position, axial or equatorial, is down on carbon 3? Axial. You can tell that because it's a down carbon. Good. And so we would continue going around the ring. The up substituent at carbon 4 should be axial. The up substituent at carbon 5 should be equatorial. And then the down substituent at carbon, oh, you know what? Can I change that? Because that's going to bother me. In carbohydrates that are actually in your body, that should have been an up group. So calling an audible, sorry. Okay. See how we did that? That's not too hard, but I'm telling you, some of you are going to be in a hurry, and I'm going to tell you in advance what you're going to do. But before we do that, let's draw the other chair. Again, the simplest way to do this is to just draw the chair with the same basic shape, only up carbons switch to down carbons and vice versa. Now, oxygen was at a down position 1. I'm going to move it to an up position. And I don't totally like that, so let's go there. Okay. So now oxygen is at an up position. Again, we're going to number around the ring in the same sense, in the same direction, clockwise. Sure. 4, 5, and 6. And then again, we go around the ring and we put everything in the right place, up versus down. So on carbon 2, it should be here. We're going through this kind of quickly. So carbon 3, it should be here. Carbon 4, the up substituent should be equatorial. Carbon 5 should be axial. Carbon 6, the substituent should be equatorial. Okay, those are the two chairs. Let's discuss, before we talk about potential, plausible distractors that you might encounter to try to lead you astray. Let's figure out how we would decide which of these chairs is most stable. Okay? So let's look at the kind of groups we've got. We've got mostly OH groups. And then here we have this weird group that's a CH2 with an OH attached to it. I don't know sort of how big that is, but if I go back to my list of A values, a CH2 with an OH attached to it probably has to be about the size of a methyl group or an ethyl group, right? Notice that when you go from methyl to ethyl, remember we talked about that additional CH3 group doesn't make as big of a difference. And notice that we know that the OH group is smaller than a CH3 group. Therefore, it stands to reason that a CH2OH group should be about the same size as a CH3 or a CH2CH3 group. Do you follow that reasoning? All right. So the CH2OH group, or the hydroxymethyl group, is about the size of, oops, I wanted a highlighter, there we go. Just based on what we talked about, that should be about the size of methyl or CH2, CH3. And then the rest of them are just OH groups, which we know. I mean, and we can estimate A values if you want, 1.7 for something that's about the size of the methyl group. And then for the OH group, it's about 1.0. So now we can sort of figure out, okay, how many OH groups are axial versus equatorial in each of these chairs. So the one on the right, I have 2 axial OHs. I have 3 equatorial OHs, and I have 1 equatorial hydroxymethyl group, CH2OH. In contrast, on the right, I have 2 axial, yes? Did I count wrong over there? 2, 2, and 1, thank you. 2 axial OHs. 2 equatorial OHs, and 1 axial hydroxymethyl. Okay, so you do the comparison. Which chair is most stable? A or B? B comes down to simply the hydroxymethyl group, doesn't it? Because you have the same number of axial OHs and equatorial OHs on either side for either chair. The big difference is that the hydroxymethyl group is axial here versus equatorial here. So yes, this is indeed the most stable chair. All right? Now, let me show you a plausible distractor. You're learning how to write tests. Let me show you a plausible distractor. I would have drawn, among many other things, I would have drawn the following molecule. And I could check the statistics, but my guess is 25% of you would have chosen this. Why does that look so enticing? Everything's equatorial, right? Why isn't that a right answer? It's not the same molecule, okay? Read the question. Which of the following is the most stable chair conformation of the molecule below? Where does this disagree? Where is this the wrong molecule? Let's number the carbons, and then you can tell me which carbons have I changed. Which ones are different? 2 is different. That's up instead of down. What else? 5 is different. Good. Down instead of up. All right? You'll learn later in 352. These are both reasonable carbohydrates. This one's called alpha D galactopyranose. This one's called beta D glucopyranose. They're both reasonable sugars, but this one is not the same as, you get it? I've distracted you with the molecule. And if all you did was memorize equatorial is more stable than axial, good, I'm good to go. I'm going to get you, okay? Behold, the plausible distractinator, right? Not my best. It's early in the morning. Maybe I need to... Perry the platypus. All right, so just be careful, all right? you will encounter something like that. That may actually have been a question on a previous exam, which I've now shown you. All right. Now, some of these issues that we're getting to, where you're seeing molecules that have the same basic connectivity, but are not the same because of where groups are placed and whether they're up versus down, this is also an issue of stereoisomerism. Stereoisomers are molecules with the same connectivity, but different shapes. And you can see now the different shapes associated with this beta D-glucopyranose and this alpha D-galactopyranose. These are stereoisomers. So we need to develop some tools for recognizing and dealing with stereoisomers. And I will say that this is what Chapter 5 is about. We're going to spend today and next time on Chapter 5 and probably move on. This is hard, and it's going to require some practice, and it's going to need to be active practice. Probably rather than you staring at a book, you're probably going to need to play with some models, okay? So if you don't have these and you've been holding out, maybe it's a good time to invest. It can be helpful in just forcing your brain to think through things. Not necessarily so helpful on the exam. It can be helpful on the exam, but it's helpful to train your brain so that by the time you get to the exam, you can draw on paper but still see in your mind in 3D. All right. So we've talked about the concept of stereoisomers, which you have heard about before. Stereoisomers are molecules that have the same connectivity but different shape. The stereo, I think, is we're using it in the three-dimensional sense. There are two kinds of stereoisomers, and only two. All right. There are diastereomers. This was a term that was invented or starts showing up about 1935. It comes from the stereo and stereomer, we're just getting rid of the iso. So stereoisomer, we've dropped the iso, and there's stereomer. Dia, I think, is from words borrowed from the Greek. It sort of means passing through. It doesn't necessarily apply here. I'm not exactly sure where it comes from. Diastereomer is best defined by what it's not. So the other kind of stereoisomer is called an enantiomer. And the enanti prefix, or enantiomer, the enanti part, if you look that up in Greek, it means opposite or on the other side, which is exactly what an enantiomer is. Enantiomers are stereoisomers that are mirror images of each other, but are not the same thing. Okay, and diastereomers are going to be stereoisomers that are not enantiomers. Okay, it's as simple as that, though you're going to struggle with that and have to work through it. Let's work on what enantiomers are. I will say, by the way, that these two terms, stereoisomers and enantiomers, are relational terms. They describe the relationship between two molecules. It makes no sense whatsoever to ask, is this molecule an enantiomer? That's like asking, are you a cousin? Of whom? Right? Whose cousin are you? It needs to be a relational term. So two molecules may be enantiomers of each other. Two molecules may be diastereomers of each other. All right? But it doesn't make any sense to ask, is this molecule an enantiomer or is it a diastereomer? You can ask, does this molecule have an enantiomer or does this molecule have a diastereomer? In the same way you could ask someone if they have a cousin, right? All right. Let's see. So let's talk about enantiomers, mirror images that are not the same thing. I have an example of that here. This model set is tiny, so some of you in the back may not be able to see it. I've got a carbon, an sp3 hybridized carbon that's attached to 4 different things: orange, purple, green, and yellow. We're trying to avoid red-green colorblind issues. And you can see if I hold them here that they are mirror images of each other, right? The mirror plane is directly between my two hands. You can see that what's on the left-hand side is a reflection of what's on the right-hand side. Do you accept that those are mirror images of each other?
Yes.
Nevertheless, they are not the same thing. How could I tell if they're the same thing? Well, I would need to move them around in space such that all of the atoms now occupy the same places. So you can do this actually forever. I can line up the purple group and the orange group, but then green and yellow are in the wrong place. Okay, well, let's try to line up green and yellow. I can do that, but now purple and orange are in the wrong place. In other words, I can adjust these, twist them around, move them around. I can do propeller spinny action. I can do pancake flip it over action. No way to make these two be the same thing. What we're trying to do, by the way, is called trying to superimpose the molecules. That's a word that sometimes shows up in questions or in descriptions of enantiomers. Trying to superimpose the molecules is just see, are they the same thing or not? Can you move all of the atoms on top of each other and they occupy exactly the same positions? You will hear the word superimpose in a definition for enantiomers that's in your textbook. They will say that enantiomers are non-superimposable mirror images. And that language, I think, is a little bit confusing. Mirror images of each other that are not the same thing. Okay? You're used to this, though you don't maybe realize it yet. You've looked at yourself in the morning in the mirror, and then you've seen a picture of yourself, and you've thought, wait a minute, that's not the same person. And that's right, because what you see in the mirror is your enantiomer. It's your reflection, and you are not the same thing as your mirror image. Now, some objects are the same as their mirror images. There are objects that are the same as their mirror images. There are objects that are not the same as their mirror images. And we need to talk about that. So, let's just draw here the objects that aren't the same as their mirror images. In this case, instead of using orange and yellow and green and purple spheres, let's just use different atoms. So I'm going to make up a molecule that has fluorine and then bromine and then chlorine. And you need to learn how to draw the mirror image of something. So I'm going to put a mirror here, and we'll use a dotted line. And then you need to get good at drawing the reflection of what we've just drawn. So here's the CH bond, and the CF bond should be going this way. The CBR bond should still be coming out at us, but angled to the left instead of to the right. And the CCl bond should be angled away from us into the page, but towards the left rather than to the right. Okay? You see how we've drawn a mirror image? Now, in your brain, you can do this with a model set, but in your brain, you can try to develop the skills to do this on paper where you say, okay, well, let me just hold on to this hydrogen with a claw and then rotate around 180 degrees, and that will give me something that looks like this. Only because I've rotated it 180 degrees, the chloro should now be in the front and the bromo should be in the back. So that's rotational motion on the page. And it can be helpful if you get good enough looking at a model set that you can do this on paper. But then I can slide this over and compare and see just what I saw with the model set. I can put the H and the F in the right position, but then the chloro and the bromo are in the wrong spots. That's one way to see that these are not the same thing, okay? So these two molecules are enantiomers. Now, I told you enantiomer is a relational term. It describes that two molecules are mirror images of each other but are not the same thing. But that property of not being the same thing as your mirror image is an individual property. And we have a different word for that in organic chemistry, and that word is chirality. So a molecule that is chiral is a molecule that is not the same as its mirror image. So a chiral is an adjective. It describes a molecule that is not the same as its mirror image. So both of these molecules that I have drawn are chiral. Okay, they are not the same as their mirror image. Non-chiral molecules are the same as their mirror images. In other words, they are their own enantiomers. So let's draw a molecule that is not chiral. A word for this you will encounter in the textbook is achiral. I think that comes from the Greek where you put an A in front of something and it means not. By the way, that's sometimes confusing for people on exams. If option A is chiral and option B is achiral, people start to hear things in their heads. Oh, A chiral, B achiral, and then get mixed up. So I won't use the word achiral. I will use the word not chiral to help you out a little bit there. A molecule that is not chiral is the same as its mirror image. Let's just replace that fluoro group with a hydrogen. We'll leave everything about the rest of the molecule the same. And then we'll draw the mirror image. Again, the CH bond should be over here. The Br is going to still be a wedge, but pointing to the left instead of the right. The Cl should be a dash and pointing to the left instead of the right. These are now mirror images of each other, but it's our task to determine whether they're the same thing or not. So, option 1, let's use the claw and rotate 180 degrees. That should make the molecule look like this, with Cl in front and Br in the back. So far, no good, but I just noticed that these two are both hydrogen. So what I'm going to do is, let's see, describing this on paper is difficult. We're going to run an axis right through the carbon in between those two hydrogens. And we're going to grab onto those two hydrogens and do sort of steering wheel action to trade their places, right? So we're going to rotate around this axis by 180 degrees. In so doing, that's going to bring this hydrogen over here and this hydrogen over there. Got that idea? Basically, we're going like this. Okay? If we do that, that will switch the places of the Br and the Cl. And suddenly, we got the same thing. That convinces us that the molecule are mirror images. The two molecules are actually the same molecule. They are mirror images of each other that are the same thing. Therefore, they are not enantiomers, but are just the same molecule. And because the molecule is not the same, because the molecule is the same as its mirror image, we will say that the molecule is not chiral. Okay? I tried to go through that slowly, but I think some of you are likely struggling to see that in your brains. If that's true, you need to get one of these and play with it until you can see that that's true. All right? All right. So, molecules that are chiral but are versus molecules that are not chiral. Why do we care about chirality? Well, because biology is made of chiral molecules. And there are consequences in biology for using one enantiomer versus another. We'll say a little bit more about that in just a second, but let's talk about stereoisomers that are not enantiomers. Go ahead. We said that they are not enantiomers. Does that mean it's a diastereomer? No, they are not even stereoisomers because they are the same molecule. So to be a stereoisomer, it's a good question. The question was, we just concluded that these two that we drew are not enantiomers. Does that mean they're diastereomers? No. You can only be a stereoisomer if you're not the same. And these two are exactly the same. Yeah?
So can you have a non-chiral enantiomer, or does that not exist?
No, you cannot. Can you have a non-chiral enantiomer? No, that doesn't exist. Two molecules that are actual enantiomers of each other are both chiral, and all chiral molecules must have an enantiomer. Yep. Okay, so let's talk about what diastereomers means. We use this as a catch-all for any stereoisomers that are not enantiomers. So let me give you a few examples of diastereomers. You've actually seen some before, though we didn't necessarily call it that. E and Z isomers. About double bonds, diastereomers. Okay? Not mirror images, but are stereoisomers. E and Z isomers about double bonds, that's a diastereomer issue. They are stereoisomers, they have the same connectivity, different shape. Maybe we should write that down there. Stereoisomers have the same connectivity, different shape. Another diastereomer issue that you didn't know you encountered, but you just actually did just a few minutes ago, was this issue of cis and trans substituents about a ring. Those two substituents, the two methyl groups there are trans, here they are cis. That's a diastereomer issue. Now, sometimes, again, as I said, diastereomer is an issue about the relationship between two compounds. We are saying nothing about whether any of these are chiral or not chiral. We're also not saying anything about whether they have enantiomers. We're focusing in on the relationship between these two compounds. We see that they are not the same, but they're also not mirror images of each other. That may not be obvious, and I'll help you with that a little bit later. Lastly, the place you've seen diastereomers before is when we talked about beta-D-glucopyranose and alpha-D-galactopyranose, and you noticed that there was a difference in which groups were up versus down. And we can still highlight the ones that are different, that's fine. There we go. And those are also not mirror images of each other, but are also not the same thing, okay? So it's getting kind of messy, even with simple definitions. So we want to give you a tool for navigating some of this, and that concept is the concept of a stereocenter. But go ahead.
I was just going to ask, is a molecule's other chair, is that a diastereomer as well?
Great question. Is a molecule's other chair a diastereomer? No. And yes. You don't like that answer, so go with the no. The reason it's not is because they can interchange via a process at room temperature. You could lower the temperature so much that they wouldn't interchange anymore, and then yes, they would be diastereomers. But no, for our purposes, we're not. truthfully, that's the same situation we're in with the double bond. You could add enough energy that the double bond would isomerize from cis to trans. So, yeah, conformational, people sometimes use the term conformational isomers to describe the relationship between the chair and the other chair. That's an okay term. We're not going to use that. We'll just describe them as two conformations of the same molecule. But no, those aren't diastereomers because they can interchange via bond rotation at room temperature. All right. Good. So let me give you a tool for helping navigate whether things are enantiomers versus diastereomers. And that tool is the concept of the stereocenter. The stereocenter is short for a stereogenic, for the word stereogenic center. If you tell an organic chemist stereogenic center, they're going to think you're trying too hard, so just go with stereocenter. Fallen out of favor in the past 40 years is the term chiral center. Don't use that. You will still hear people use chiral center. It's not a great term for reasons that are, again, like delving deep into the OChem lore, and you just got to indulge me on this one, okay? I'm not going to use the term, and if you use chiral center to me, I will twitch a little bit and then decide that I can move on with my life. All right, stereocenter is, we'll define it more specifically for our context, though you can define it a bit more broadly, but for our purposes, it's going to be an sp3 hybridized carbon attached to 4 different things. Okay? Asterisk, does it have to be a carbon? No. But it does have to be 4 different things. Second, what is different? And we're going to talk about that. It's going to be different all the way out. So the simplest stereocenter that you can see here is this carbon, and I'm going to highlight stereocenters in pink. This carbon is a stereocenter because it is attached to 4 different groups. You see hydrogen, fluorine, chlorine, and bromine. When you see a stereocenter, a carbon that's attached to 4 different groups, that is a place at which there are 2 possible configurations. The one on the left where we have enantiomer 1, and the one on the right where we have enantiomer 2. Okay? So we're going to need a way, and you've seen a concept like a stereocenter before. We didn't call it a stereocenter, but we just called it a double bond. When you have a double bond, because you can't rotate around this double bond, there are 2 possible configurations for the double bond, E and Z. We're going to see the same thing with a stereocenter. There are 2 possible configurations. Go ahead.
So with the double bond, isn't it 2 p orbitals hybridizing, so it wouldn't be an sp3?
That's right. We won't call this a stereocenter. Some people do, but I'm just illustrating that like the double bond, a stereocenter has 2 possible configurations. Yeah. Okay. So let's talk about how, like we had before with the double bond, 2 ways, 2 configurations, and we had a way to say which was which. We're going to have the same thing for each stereocenter. And the rules are actually going to be, for assigning one configuration versus another, are going to be exactly the same as for assigning E versus Z. The only difference is now you've got 4 groups instead of 2. So I'm going to copy those images here. And what we're going to do is, having identified a stereocenter, you now need to rank the groups attached to the carbon, the stereocenter, from 1 to 4 based on an atom by atom comparison of atomic weight. Some of you got confused with E and Z. I feel like most of you resolved those problems pretty quickly, but we're going to use the same tie-breaking procedure that we used for E and Z for these stereocenters. In this case, it's pretty simple. Hydrogen is priority group 4 because it's the lightest. And then fluorine is 3, chlorine is 2, and bromine is 1. All right? See how we did that? Just ranking them in weight. If there was a tie, we would ask what other things are they bonded to in the same way we did for E and Z. We'll practice that maybe a little bit. Now, here's the difference. With a double bond, we didn't have to do anything else. We just assigned the priority groups on either side, and then are they on the same side or opposite sides. With a stereocenter, what we have to do is align the molecule so that the lowest priority group, the bond between the stereocenter and the lowest priority group, is facing away from us. You can do this if you want. This is one way to do this, by sighting your eye in the plane of the page. I can never resist drawing evil Sith eyes when we do the Newman projection. This is Anakin. I hate you! I made the mistake of showing my youngest son Revenge of the Sith when he was like 4, and he got kind of scared by Anakin being... He's gotten over it, I think. I don't know. But I'm like, buddy, we were all sad when Anakin fell to the dark side, so just, I don't know what to do for you. So we draw the carbon in the middle. The hydrogen's going back into the plane of the page. We can't see it. The bromine should be here because we're sort of tipping ourselves down into the plane of the page and looking at it. The chlorine should be to our right and the fluorine should be to our left. If that's hard, you need to work with one of these until you get it. All right? So again, you've got groups 1, 2, and 3. All right, then you go from 1 to 2, 2 to 3, draw an arrow, and then 3 back to 1. And then you ask, is that rotation clockwise or counterclockwise? In this case, it is clockwise. Clockwise rotation means we're going to call this stereocenter R. R comes from the Latin rectus, which means right. Okay? And using a similar method, we can make the same type of assignment over here for the other enantiomer. If you did that and used our same Newman projection method, oops, I just want to copy, not move, then you would see, again, a bromine here, a fluorine to the left, a right, and a chlorine to the left. 1, 2, 3, an arrow from 1 to 2, from 2 to 3, from 3 back to 1. Then you ask, is that clockwise or counterclockwise? It's counterclockwise, so we will call it S. That comes from the Latin sinister, because left-handed people are evil. I'm just kidding. It's not really true. My son, the one that hates Anakin, is left-handed. So please do not take that personally, okay? That was a joke. I'm sorry. I don't know why sinister happens to be the term for left in Latin, but it does. In any case, you've got R and S configurations for stereocenters. We're going to use that to talk about chiral molecules. Now, just a word, I'm not going to be here on Friday. We won't have class as normal. I will record a lecture and post it on Learning Suite and YouTube, and you can watch it there. You won't have the opportunity to ask questions, but you can ask via email and I will respond. So next time we will meet will be Monday. Watch for that posted lecture soon, and I will see you Monday.